You wake up in a mysterious world of darkness and labyrinthine passages. All you can do is helplessly walk into walls and, bump after bump, familiarize yourself with the world you found yourself in. This is probably how a vacuum object feels when initialized in my code, vacuum.py. Or, more accurately, this is how the AI agent that controls the vacuum cleaner would feel if it had emotions. It does not. But it does have the power of search algorithms on its side. Today I'll be going into the code to explain how this poor AI can navigate in a world of air, blocks, and dirt. The code is written in Python and consists of 4 classes, an example function, and a dictionary of global constants. The first class is called UI and allows us humans to understand what is going on in the AI. I use the library matplotlib's visualization of matrices as grids of pixels to represent the world of the vacuum cleaner, as well as the AI's own knowledge about the world. I also give some indication of how the AI is searching around, both by laying some information over the knowledge space, as well as by reporting some basic information that the AI deduces. The colors used to represent various elements of the world are given by the global dictionary constants. I won't go into more details since this does not directly use search algorithms. The second class, Vacuum World, encodes the desolate world that the vacuum cleaner will be cleaning. The world is represented by a grid where each square can be air, where the vacuum can traverse, a block which blocks the vacuum, or dirt, where the vacuum can traverse and clean. I've added methods to randomly generate a world, which is what will be used in the example function. You can also populate this world with vacuum cleaners, and there are methods for checking if a vacuum is on a dirty square, using the vacuum on the square, and attempting to move the vacuum in a cardinal direction. The third class, Vacuum, is a small class that gives the user control over a single vacuum cleaner. It's objects of this class that are handed to the AI agent. Which brings me to the last and most interesting class, Single Vacuum AI. Objects of this class start with an assigned vacuum cleaner, as well as some helpful information, the shape of the world grid, and the initial position of the vacuum. Technically, we could have started without any extra information, but this somewhat simplifies the code and the visualization without affecting the algorithms used. The general idea remains the same. We start out in an unknown world, and we try moving around to discover where we can or cannot go. The computer science problem that I'm describing here is called online graph exploration. Graph because a world grid is a type of graph, where each accessible square is a vertex, and the edges connect squares sharing a side. Exploration because, as a vacuum cleaner agent, your goal is to fully explore the space to make sure that no dirt remains. Online because we are learning what the graph is as we go. In this situation, the optimal strategy is the greedy approach. Here is an article that you can check out for more technical details. In this case, greedy means depth-first search. We tell the vacuum to move forward into the unknown until it gets completely stuck, and then backtrack to the last square where there is still some unknown neighboring square. The algorithm ends when we backtrack all the way to back before the start. And since a given explored square has at most 3 unknown neighbors, we can only backtrack to a given square at most twice. Thus, the vacuum cleaner traverses at most 3 times the number of squares on the grid, which is the same big O complexity as an optimal path if we knew the entire grid beforehand. There's one more thing I want to describe, and that's the backtracking. The simplest way of backtracking is to just retrace your steps. However, this may not be the shortest way back. It's easy to determine the latest square with unknown neighbors just by checking the knowledge space, and then to find the shortest path to that square, we use the A-star search algorithm. This algorithm starts at the starting square and maintains a list of candidate squares with a cost associated to each square. The cost is the sum of the backwards cost, the shortest path length from the starting square, and a heuristic, here the one norm distance to the target square. The algorithm is interested in the candidate square with the lowest cost. If this square is not the target square, then we remove it from the candidates and add its not yet considered neighbors as candidates, calculating their costs. In particular, the shortest path length from the starting square must be the shortest path length of the original candidate plus 1. Noting this, we also record where each candidate square got its shortest path from. Once this lowest cost candidate is the target square, which will happen at some point, we can follow the path of previous squares to get the shortest path from the starting square. Okay, I think that's enough script reading. Let's look at the vacuum cleaning agent in action. Okay, so this is what the actual UI looks like. So here's on the left, we have the world view, and on the right, we have the AI's knowledge. And so currently I haven't initialized anything, and the way that I've configured the code currently, I can just click on any key and it will increment the code by 1 step. So now we're populating the world with dirt and with blocks. And so already you can see that sometimes the randomly generated blocks will create these small spaces that won't be accessible if the vacuum is out in the open. The last thing we do is we add a vacuum, and then we initialize the AI. So on the right here, we have a log that has vacuum position, as well as a current status, status more or less. In light pink, I've represented the depth first search. So this is the current path that the vacuum is exploring. This is the branch in the search tree. And then in dark pink, there'll be a star, which will appear at some point. Around where the vacuum has explored, we have light blue. So these are squares that the AI knows exists, but does not know the value of. And then further out are inaccessible squares. So these are squares that the vacuum cannot get to without passing by an unknown square. So at the beginning, the vacuum just kind of moves around. Here, it just landed on a square of dirt. And so when it leaves, it will clean it. And so this is done in the code. And the way that the vacuum chooses directions, it's kind of biased towards going up, which isn't really a problem, since, as I explained, the greedy approach is the best approach. So now it starts moving left until it hits this block. So now it has been blocked. So it's updating the knowledge by adding a square here, and now it looks for another square to go to. So it's going to go downwards. And then I believe it'll probably go left here, yeah. And it gets blocked a few times. And now it is completely blocked. So the AI knows that it's blocked, and it will start backtracking with a star. So a star starts with a candidate, which is the neighbors of this square where the vacuum is. And it checks if this is a target square. And the target square, remember, since we're doing depth first search, is the last square that still has an unknown neighbor. So it's this square over here. So the current dark pink square is not good. So it's going to continue searching, and now it has found it. So this is the path that it has found, and the vacuum now travels to that place. And now we continue with depth first search. And once again, the vacuum very quickly gets blocked. So it will continue searching, and this time it only has to backtrack 1 step. So a star finishes in 1 step. And then we continue, blocked once again, and now it needs to backtrack a little bit more. So it starts searching in all directions, since a star does search in all directions, but it favors the correct direction. And now it's found its path, and now it can continue. And so at this point, I think I've kind of covered all of the possibilities at the beginning. And so now the vacuum is kind of in the middle of this large explored space, and it is searching for the latest square with an unknown neighbor. And so it's not easy to see, since I didn't make it very clear how this branch looks exactly, but I think this is probably the last square with an unknown neighbor. So it will start searching bit by bit. And it has determined, so this was actually the last square. So it traveled there, and then once again, it got blocked. So it's going to go to the last square with an unknown neighbor. And so now you can see that we've backtracked quite far. Remember that the vacuum started at this square, and then it did this whole path, and now we've backtracked to here. So now we'll do, this is kind of the final stretch. And now the vacuum is done, so it is searching for its home where it started. And now it is done. Okay, so now I'm running the same code, but on a much larger grid. This is 70 by 70. And so as you can see, the vacuum is going at lightning speed, cleaning everything and backtracking. And now it is already done. So this algorithm works, and it showcases two pretty interesting algorithms for online graph exploration. So depth first search that actually does the exploration, and then the A-star search algorithm, which allows for faster backtracking than what might usually be expected for depth first search. And the code is available on GitHub with the link in the description. And that's it. Thanks for watching.